To understand today's topic, we need to recall some of the previous topics. First of all, we should be knowing the electrostatic potential of point charge. We know that if we have point charge q and if we want to find out electric potential at distance r, it can be given as V is equal to kq by r. We also know that electrostatic potential of point charge depends on the magnitude of charge, distance of the point, and medium. If you change medium, potential will change. And if you have charge q given in some coordinate system, say at position vector r, and if you are interested in finding out potential at some point p with position vector r prime, the potential of charge q at point p can be given as V is equal to kq upon mod of r minus r prime. So with this topics clear, we can move forward. Consider an electric dipole with its charge minus q at point A and charge plus q at point B. Let the center of the dipole be O, and let the separation between the two charges minus q and plus q be 2a. And we want to find out the potential of this dipole at some point. So obviously we'll have to define point. Let the point be P. Where is point P? Let it be at distance r from center of the dipole. Whenever you find out electric field or potential of dipole, it is always measured from center of the dipole. So let us consider that point P is at distance r from center of the dipole. And then how much is the distance of point P from positive charge? How much is the distance of P from negative charge? So let the distance be r positive from plus q and r negative from minus q. Now, not necessary that you label it as r positive and r negative only. You could label it as r a or r b. It's okay. Symbol is not very much important, but there has to be two different symbols. So for now, let us consider it to be r negative and r positive so that we can relate it with negative and positive charge. Now let the angle between dipole moment and position vector of P be theta. Now where is the direction of dipole moment? We know it is from negative charge to positive charge. So in this case, it is from A to B. This is the direction of dipole moment P, and with respect to this P, where is the point of interest? So this angle is important, and with this angle potential will change. For now we label it as theta. So in our diagram, this is where we have our theta. And can I say that angle at point A is also theta? No need to frown, let me make myself clear. Consider this situation where I have plus charge at one end and negative charge at other end, and I have some point P. So obviously if I draw angles, I know that these two angles are not same. If one is theta, other one cannot be theta. But what if this is how I have my dipole, and then I consider the point P to be at very large distance. Now in this case, if you look at the angle theta, this theta will be almost same. So for now, the angle at point O and angle at point A both are labeled as theta, and later on we'll make assumption that 2a is very less than r. So this condition is satisfied, so don't worry about that. Now let us enter into maths part. How to find out potential at P point? So very simple. You have two charges, so first find out potential of first charge at point P, then find out potential of second charge at point P, and then sum up the two. And we know how to find out potential. It is kq by distance. So how much is the potential of negative charge at point P? Kq by distance. How much is the potential of positive charge at point P? Kq by distance. We have charges known, we have distances known, so it should not be very difficult. Let us try. I forgot one more thing. We consider foot of perpendicular from point B on AP. Why to do this? we'll come to know about that soon. So here is the situation, and now we know that dipole moment in this case can be given as P is equal to Q into 2A. So here is the first equation of our derivation, and then potential of negative charge at point P is kq by distance. How much is the distance? R negative, and charge is minus q, so it will be minus kq by R negative. Let us label it as VA. And similarly, potential at point P due to positive charge will be kq upon R positive. Okay, and then resultant potential can be given as VA plus VP. So potential at point P VP, if we denote it as, then it is VA plus VB. Let us simplify it further. So now from the figure we have AM is equal to AB cos theta, or else you can say that cos theta is adjacent by hypotenuse. Who is adjacent of theta here? AM is the adjacent. I am talking about triangle AMB. So look at triangle AMB. Okay, and apply cos theta formula. So cos theta is AM upon hypotenuse, that is AB. Okay, and let us recall previous equations. So previously we have P is equal to Q into 2A, dipole moment is Q into 2A, first equation, and then we realize that potential at point P is kq by R positive minus kq by R negative. Okay, so if we simplify it, we come to know that kq can be taken outside, and it comes out to be 1 by R positive minus 1 by R negative. And taking LCM, this is what we get. Now, as I said earlier, suppose if the point of interest is at very large distance, then the angle is suppose here I have my negative charge, and here I have my positive charge, and then if I take foot of perpendicular and look at the condition, this is my dipole, this yellow one is my dipole, and this line is foot of perpendicular, but with that line what I am indicating is that this gap is the difference between R negative and R positive. So for our figure I can say that AM is the distance which is the difference of R negative and R positive, and that is what we want here in the numerator. R negative minus R positive is the difference between the two distances, and then I can replace it by AM. Moreover, when you are talking about the denominator, what is the product of R positive and R negative? So when you consider point P at very large distance, almost these three are almost same. R negative is slightly more than R, R positive is slightly less than R, so you can replace these two with R and R. So denominator will be R. So let us try out. We'll replace numerator R negative minus R positive with AM, and we have AM is equal to AB cos theta. Not only that, we also know that AB is 2A, so actually AM can be written as 2A cos theta. So numerator will be 2A cos theta, and in denominator we'll take this as R and R, so denominator will be R square. But this is possible with the assumption. Okay, what is the assumption? Assumption is when R is very greater than 2A. If the point P is very close to the dipole, this is not valid. So you can take it as one of the limitations. So if point P is very close to the dipole, then second equation is the equation for potential. But most of the time, these dipoles are created by molecules of like HCl or H2O, and hence the dipoles are very tiny. So mostly the point where we are finding out potential is at very large distance compared to the dimensions of dipole. So R very greater than 2A is very much realistic condition. So with that assumption, as I said, the denominator becomes r square, and then we can write our second equation as kq with 2a into cos theta in numerator and r square in denominator. But now we know that q into 2a is dipole moment. Look at our equation 1. So now we'll write this 2 into cos theta. Replace q into 2a with p, and then our equation is kp cos theta by r square. Now we know that if we have a dot b, suppose if you have dot product of two vectors a and b, how do we write it? We write it as a b cos theta, isn't it? But what if b value is 1? Suppose magnitude of b is 1, then it will be a into cos theta only, isn't it? So I can assume that here I have 1, and I have one more vector whose magnitude is 1, and then I can write this expression of Vp, potential at point P, as dot product. So you can write it as P dot unit vector R. Okay, so this is another way of expressing it. You can always express it as Kp cos theta by R square, or else you can write it as K vector P dot unit vector R upon R square. So equation 4 is the required equation of dipole, potential of dipole at given point. But as I said, this is having one major limitation, that we assume here that point where we want to find out potential is at very large distance compared to the dimensions of dipole. But as I said, that is a very realistic condition. So in most of the cases, we should be able to apply it. Now let us compare electric field of dipole with electric potential of dipole. So in case of electric field, if you remember, we had two different formula for electric field. On axis, we can find out electric field with this formula 1 by 4 pi epsilon 0 2 times dipole moment upon distance cube. And on equator, if you have another formula, E equator is 1 by 4 pi epsilon 0 dipole moment upon distance cube. Luckily here, we have only one formula for potential of dipole, and that is k vector p dot unit vector r upon r square. So in case of electric field, the electric field depends on distance of the point where you are finding out electric field, and potential also obviously depends on the distance where we are finding out potential, but the dependence is not same. The electric field of dipole varies as 1 by r cube, distance cube, whereas the electric potential of dipole varies as 1 by r square. So we can say that the potential of dipole varies slightly at less rate compared to electric field. Electric field drops drastically if you change your distance from dipole, if you go away. That is not the case with potential. It also decreases, but not as fast as electric field does. So let us conclude now. So now we know that electrostatic potential of a dipole can be given as Vp is equal to Kp cos theta by r square, or K vector P dot unit vector r by r square. And as I said, what is theta? Don't forget what is theta. Theta is angle between dipole moment and the position vector of point, that is r. And so if you are on the axis of dipole, the theta will be either 0 or pi. So if theta is 0, then what is cos theta? Cos theta will be 1. And if theta is pi, in that case, cos theta will be minus 1. So cos theta, if it is plus 1 or minus 1, potential will be plus or minus kq by r square. But if you are on perpendicular bisector of dipole, potential will be 0. So this was not the case for electric field. There also we had variation, but here variation is with angle, not only with distance. With orientation of the point also potential changes. So let us try to understand how orientation of the point affects the potential of dipole. So let us consider a dipole with negative charge on the right side and positive charge on the left side. This yellow dot is the center of the dipole, and we want to find out potential of this dipole at some point on its axis. So what I'll do is I will move this point on this path, and we'll see how potential varies. See, if this is distance r, there should be some potential. Now, how much is the potential if you are at same distance but at some other angle? How much is the potential if you are at same distance but at some other angle? Okay, so in first situation, this is the dipole moment, and this is the position vector. So what is the angle between P and R? It is 0. Okay, angle between P and R is 0. So according to this equation, what is cos theta? Cos theta is 1. So potential will be plus kq by R. As you go here, as you follow this path, and when you come to this, what is the angle between R and P? If this is R, this is P, angle will be 90. Cos 90 is 0. So at this point, potential should be 0. There is one more reason why potential should be 0 here. See, potential due to positive charge. Potential due to positive charge here will be plus kq by distance. Potential due to negative charge here will be minus kq by distance. So what is the resultant potential here? It will be 0. Add the two and answer will be 0. So whenever you are on perpendicular bisector of the dipole, potential has to be 0. And on this side, potential should be positive. On the other side, potential should be negative, because in all this region you are close to negative charge, whereas in the left side of this diagram we are close to positive charge. So potential should be positive. So can we plot a graph of potential versus angle? And if we plot it, what will be the nature of that graph? Let us try to understand. So here I am taking potential on vertical axis and angle on horizontal axis. So horizontal axis is 50 degree, 100 degree, 150 degree and 200 degree. And this is where we have our 90 degree. Okay, so as this point moves from axis to bisector, how the potential varies? Look at this progression. Potential reduces slightly, and when the point is here, when you consider point to be on bisector, potential will be 0. Why? Because potential due to positive charge here is plus kq by r. Potential due to negative charge here is minus kq by r, so resultant is 0. And why this fall? Because as you move from positive charge to this point, negative charge is increasing its influence, and so resultant potential reduces. What will happen now? As I move further, what will happen? I am going close to negative charge, so my negative potential will increase. I am going away from positive charge. And hence, as you move, look at this dot, we are going down, and we'll come here and look at the potential. It is decreasing. Okay, so exactly when you are here, the potential will be negative. How much? Minus kq by r. How much is the potential here? Plus kq by r. So that is how potential of dipole varies as you change angle. So that was the topic, electrostatic potential of dipole. I hope you could understand it. Thank you.